So today we're going to talk about convergence and divergence of infinite series, and I'm going to go through a complete example of how one would go about creating the mathematics behind this whole thing, essentially involving a conjecture. To begin with, I need to talk about the sigma notation. The Greek letter sigma stands for summation here, and k is referred to as an index on the sequence of terms, a k, and this is what we mean by summing the term from the nth term up through the nth term. But it takes a little bit of doing to figure out exactly how to interpret these things and what it means. So, for example, here we have sigma k goes from 1 to n, and the term 1 is there. So what is it, and how do we interpret this, and what does it mean? Now, the way to look at this is that this 1 is a constant, but it's a stand-in for each of the terms that's going from 1 to n. So for example, in this case, a1 is equal to 1, a2 is equal to 1, and so forth up to a, so n is equal to 1. So what this means is that it's 1 plus 1 plus 1, and so forth, all the way up to the last term, which is 1. And we do this how many times? N times. So we have n ones, and so it all adds up to n. And that's the interpretation that we give to this when we have a constant in there. Now, occasionally we have a situation where we'll just have terms from, say, 3 to 7, and the question is, well, what does that add up to? We can use our fingers to count up and determine what's going on here. Some people take a look and see the 3 and the 7, they say, aha, so it must be 7 minus 3 is 4. And we have to be careful about this, though. So one way to look at this is to consider this as the summation as k goes from 1 to 7 minus the summation as k goes from 1 to what? 2. And so from 1 to 7 is 7, and from 1 to 2 is 2, and so altogether it's equal to 5. Of course, if the numbers are big enough, then you don't want to use your fingers. We can't do that anymore. Okay, so let's talk about what it means for an infinite series to be, or a series to be convergent. So we have a sequence of terms, an, and the nth partial sum, referred to as s sub n, is going to be the sum of the first n terms. And if this particular sequence of partial sums is convergent as a sequence, that is, this limit exists. And that's referred to as the sum of the series, or the so-called limit sum, which is the result of the sequence of partial sums. Of course, if it's not convergent, then we say that it is divergent. Now, let me just backtrack a little bit here. When we add two numbers together, addition is defined between two numbers. And if you have three numbers and you want to add them, you can add the first two, get a new number, and then add the third one onto that. And you can keep on doing that in a finite number of times. But at a certain point, if you have an infinite series of terms, you can't literally add them all up one at a time. It's not possible. So instead, we talk about taking the limit, what would happen in the limit. And that's why I refer to it as a limit sum. Some people refer to it as an infinite sum. So that's what we're doing here, working with infinite items. So here we have a series, 1 over k times k plus 1 as k goes from 1 to infinity. And the claim is that it converges to 1. So we'd like to show that that's the case, fully and completely. So how do we do that? Well, first off, it would be nice if we can get a formula for the sequence of partial sums. So to do that, we take a look experimentally at the case where we just have one term. And so let's see, as k goes from 1 to 1, so the only term there is the 1 over k times k plus 1 when k is equal to 1. So you replace that, and that's equal to a half. Okay, and then you take a look at the next term, k goes from 1 to 2. And so you take the half and add the next term, which is 1 over 2 times 2 plus 1. So that's 1 over 6. And if you add these together, you're going to get 2/3. And if you do this again, take the 2/3 and add the next term. So k is equal to 3. So it's 1 over 3 times 3 plus 1. So that's going to be 2/3 together with 1 over 12. You put them all over a common denominator, and you get 3/4. Now, you take a look to see if you have a pattern emerging. So the first time we had a half. The next time we had 2/3. And the next time we had 3/4. Let's take a look at one more. So when k is, if we add up the first 4 terms, we already have 3/4. And then the next term is 1 over 1 times 1 over 4 times 4 plus 1. So that's 1 over 20. And if you add that to 3/4, you're going to get 15 over 20 plus 1 over 20 adds up to 4 over 5. So the next term in this collection of sums is going to be 4 over 5. So at this point, can we make a conjecture as to what this is going to be if we keep on going up to the nth term? So the first term had a 1 in it, the second term had a 2 in it, the third term had a 3 in the numerator, and the fourth term had a 4 in the numerator. And so we can conjecture that the numerator has n in it if you have n terms as the sum. Now, the denominators were merely one more than the numerators every time. So we can conjecture that the denominator is going to be n plus 1. So that's our conjecture for what this series is going to look like. How do we prove a conjecture like this? Well, you recall we had the principle of mathematical induction. And that's what we would use to validate that this partial sum is equal to n over n plus 1. So how does that work? Well, you remember the first term, it has to work when n equals 1. And so n over n plus 1 is going to, for n equals 1, is 1 over 1 plus 1 is 2, 1/2. So that checks. It is valid when n equals 1. Next, we suppose that it's going to be true in general for the nth term. That's the so-called induction hypothesis. And we need to prove that it's true for the succeeding term, the n plus first term, which if you substitute in to the formula n plus 1, you get n plus 1 over n plus 1 plus 1, which reduces to n plus 1 over n plus 2. So we want to show that that's true. And how do we show it? Well, we take this summation and break it up into the sum of the first n terms, which we're assuming is correct, and we need to add to it the next term in the summation. So we replace the induction hypothesis term with n over n plus 1, and then we have to add it to this fraction, 1 over n plus 1 times n plus 2. So now it's a fair amount of algebra in order to keep on going. So we're going to put everything over a common denominator. In this case, it'll be n plus 1 times n plus 2. And in order to do that, you can multiply the first term by n plus 2 over n plus 2. And that'll give us the correct denominator. And then we want to add these terms. So the denominator is exactly what I said it is, n plus 1 times n plus 2. When you multiply n times n plus 2, you get n squared plus 2n. And then the plus 1 comes from the second term. Now that numerator factors into n plus 1 squared. And sure enough, you can cancel that with the n plus 1 downstairs, and you're left with n plus 1 over n plus 2. Oh, that's exactly what we were looking to get. So that checks. So that proves, using mathematical induction, that that formula is correct. Great. But our goal is to eventually prove that this limit, in fact, is equal to 1. Well, we've converted this infinite series into something that we used to work with finding a limit of a sequence, and that's much easier. So let's go through the definition. The definition says that this limit is going to equal 1 if and only if for any epsilon greater than 0, this is the definition, there's a positive integer n, capital N, and if you take any other integer bigger than capital N, then this inequality will hold. Now you remember that in order to make these things work, we always start at the end and play around with the term inside absolute values here. So we want to reduce that in some sense. So n over n plus 1 minus 1, put everything over a common denominator, which means write 1 as n plus 1 over n plus 1, and then bring them together, a little more algebra. And then when we do this, we end up with the absolute value of 1 over n plus 1, which is the same thing as 1 over n plus 1, because it's positive. You drop absolute values. Now, if I were to cross-multiply, I'd end up with a term like 1 over epsilon is less than n plus 1. And if you would isolate n on the right side, you'd have 1 over epsilon minus 1. And this could be a negative number. And even if you use the ceiling function with it, you'd end up with 0, which is not a positive number. We're supposed to find a positive number. I'm not saying it's bad or wrong, but it's not a clean way to write things. A better way is, the suggestion that I have here is that we require, and we can, a stronger inequality. Instead of n plus 1 should be bigger than 1 over epsilon, we require that n be bigger than 1 over epsilon. And that avoids the messy situation with possibly negative numbers that we have. So here's the proof. Given epsilon greater than 0, we can choose n to be the ceiling of 1 over epsilon. And if n is bigger than capital N, which is bigger than 1 over epsilon, if I were to add 1 to the side on the left here and on the right there, I'd get n plus 1 is bigger than 1 over epsilon plus 1, which happens to be bigger than 1 over epsilon. And that's what I wanted. Because as soon as I have that, you can cross multiply, and you can see that epsilon is going to be bigger than 1 over n plus 1, which, and now we just backtrack and show that it satisfies the original inequality. This is the same thing as the absolute value of n minus n plus 1. Break it up again, and finally we get the term that we started with over here. Epsilon is bigger than that term, and that completes the proof. And so that's one full and complete story with regard to showing convergence of a series.